What's up, goons, goblins, traveling merchant? I don't know. What else do you find on a highway? Goons, goblins, trolls, um roving bands of bandits? I don't know. What's up, you guys? Today we're going to talk about the third and final keystone of kinematics. This is the end all be all of mechanics. Once you have finished this unit, you're going to have all three fundamental building blocks for all of mechanics. Once you have this unit, you're going to be able to calculate the rotation of stars, the collisions between two massive objects, the energy of a whole bunch of stuff. The world is your oyster, and anything that moves within it is in your domain. Um, Basically, momentum is the third and final most important thing for mechanics. And once you have forces, energy, and momentum, you are basically an engineer. You have everything you need to know to do everything that moves. Um, yeah, it's gonna be tight. You're gonna love it. I'm excited for you. You know what I mean? When I teach kids other stuff, I kind of I feel like I'm just like, all right, here's the process. Look at this. Here's a pretty picture, right? But you guys, I'm like transferring power. You know what I mean? I'm like passing the scepter to my heir and saying, "Take care of the kingdom. It's been great." You know what I mean? This is tight. You guys are learning something that got people to the freaking moon, bro. How tight. You know what I mean? Yeah, physics is so tight. So, all right, let's dive into it. We're going to talk about momentum and impulse. So, let's start with some vocabulario. So, momentum is a very tricky thing to describe. Momentum is not dissimilar from energy. It is also telling us how much an object is moving. But there's a key distinction between momentum and kinetic energy. Momentum is a vector. So, for all of the reasons that kinetic energy was tight, it was cool because it let us solve a bunch of weird problems without worrying about all the stuff in between, right? We had a ball flying and we want to know what happened at the top, and we didn't want to go through the trouble of calculating times and velocities and measuring accelerations and using displacement equations. So we said, all right, all this kinetic energy turns into all that gravitational energy. Bada bing, bada boom, it's up there. You know what I mean? Momentum is tight for exactly the opposite reason. Momentum is tight because it helps us study those messy interactions that we completely ignored with energy. It takes into account direction, it takes into account what happens when this thing hits that thing. Um, it's basically measuring the same idea as kinetic energy, but like the messy side of it, right? Both of them measure how much an object's moving, but kinetic energy blatantly ignores directions and it just transforms into other stuff. Momentum also measures how much something is moving, but it takes into account which direction is that stuff moving, how fast is it going, how heavy is the object. It's so cool. So think of momentum as how much something is moving and how much it wants to keep going that way. Okay. Impulse, if momentum is similar to kinetic energy, impulse is work. Uh, Impulse is to momentum as work is to energy. Impulse is the absolute change in momentum, and it's also a vector. So the reason it's a vector is because it's telling me how much my momentum changed. So if I know how my momentum changed, what if I have some momentum this way, and then later I have some momentum this way? The change needs to tell me not only how much the length of this thing is, but also how this thing turned, right? The change needs to incorporate the direction because the thing we're measuring has some direction. The reason work isn't a vector is because kinetic energy isn't a vector. So there we go. There's the two things we gotta know about. So it's all well and good to like, ooh, look how shiny this new toy is I have. But let's go learn the nitty-gritty of it, okay? Let's dig our fingers into some maths. So we're gonna look at some equations on how momentum and impulse are defined. And then I'm going to talk to you for a while about how do I use this shiny new toy. Please, Papa, teach me how to transform Optimus Prime from a truck into a gorilla. That's the right. It's cool that he's a truck, but I want him to be a gorilla. Show me how to use the shiny new toy. Disclaimer. Okay, well, I've got your attention. My dog just growled, so if your eardrums shatter in like the next 2-3 minutes, something's bumping around outside. My apologies. But you know I can't do this in 2 takes. This is live, baby. This is all original. All right, formulas. So here are 2 formulas. Disclaimer, there is a third one that we will see on another slide a little bit later. I think the next slide. But here's the 2 main definitions we need to know. This, you're going to say, Mr. Brown, where's momentum? This is momentum. Momentum is P, for some reason lost to the aeons past. No, I'm just kidding. I think it's something to do with like the word they use for momentum in Latin, like way back in yonder years. It started with a P. I don't know how it turned into an M, but it did. So we use P for momentum. These little arrows just tell us what things are vectors. So momentum's a vector, mass, not a vector. Velocity, a vector. Okay. All right. The units for momentum are the units for mass, kilograms, times the units for velocity, meters per second. So a kilogram meter per second is the unit of momentum. And unfortunately, no physicist has come up with something so groundbreaking and earth-shattering about momentum that they've gotten the momentum unit named after it. But I don't know, maybe you can discover something new someday. Make sure it has to do with momentum, and then we'll slap your name on it. We'll call it the Hernandez, or the Carrion, or the Mitchell. You know what I mean? Or some other. Or if you get a Nobel Prize for the momentum, right? You maybe they'll let you name it, right? They'll be like, "What do you want to name it?" And you should come up with something really stupid for it. You should be like, "I want to call this thing a Zuppendorf, or a Snaggle What's It." You know what I mean? Make people be like, "How many Snaggle What's It's are you measuring there, Keith?" And they're gonna be sitting in their lab with their Snaggle What's It-o-meter. You know what I mean? How funny would that be? That'd be tight. All right, so here's momentum. It's mass times velocity. Equally cryptic, impulse is a J. And it is the average force times time. Yeah, there you go. That's the way it is. Here's the important bit that we need to amend on this equation here. Impulse is equal to another very, very important thing. Impulse is also change in momentum. So important. This is going to let us solve so many problems. So
Momentum is mass times velocity. Impulse is the change in momentum. So it's equal to the average force times how long that was applied. It's also equal to mass times delta V, if you want to think about it that way. As long as the mass isn't changing, that is. So we'll futz around with this a little bit later, but we gotta be creative about it. So here's our equations. Let's talk about why momentum is such a powerful tool for physicists. In a closed system only, and when we say closed system, we mean if I'm looking at this stuff, I got like a ball and a block and a person and like maybe a little butterfly, a giant butterfly, actually. It's as big as that person. And like some fire. You know what I mean? If this stuff is in my system and nothing else comes in, no intruders and no quitters, then very, very much like our beloved energy, in a closed system, the total amount of momentum is constant. What I just told you is momentum is conserved. This is probably top 5 most powerful ideas in all of physics. F equals ma. That's the power stone. Energy is not created or destroyed, only conserved. That's the time stone. Momentum is concerned. That's the soul stone. Okay? So we've almost got all of them. We'll talk about electricity and magnetism and all that stuff later, but we're getting there, all right? We're ready to snap our fingers and make a new galaxy pretty soon here. So this is so useful for solving problems because it allows us to infer the momentum of stuff that we don't observe. If I know that this object went over there and did something, and then this object comes flying out with some other speed, I can figure out what happened over here where I didn't see because I know the momentum of this thing going in, and I can probably measure the momentum of this thing coming out. It paints a beautiful picture. Right? We got some trees, like a little dude, a little dudette. Right? I can tell what's going on over here without even looking at it. It's so powerful. So the way we conserve momentum, the equation we're going to use is the sum of momentums initially. So this is all the momentum in the system. It's the momentum of this thing. It's the momentum of these people. It's the momentum of that thing before the interaction happens. That equals all the momentum added together after the interaction happens. And that total amount of momentum must be the same in a closed system. If you have an open system, then we're probably going to need to invoke impulse. But in a closed system, momentum is conserved. Okay, so let's go talk about how do I use these? Because right now, Mr. Barton, you're just spitting poetry at me. You're telling me how much you love these things that are weird and bizarre and a little abstract. You got to break it down a little more concretely for me. How do I use this junk, Mr. Barton? I believe you that it's beautiful and useful, but I've got naive little eyeballs and I can't see it yet. So let's go take our naive little eyeballs and point them at Babby's first momentum picture. Okay, so how do I measure momentum? Unfortunately for us, there is no such thing as a momentometer. There is no device that you point at something and it tells you the momentum. Okay? Momentum cannot be directly measured. What we have to do is measure the things that give an object momentum. So we need to measure the mass and the velocity of the object. How you want to do that's up to you. So let's say I've got this mass right here. If you want to hook this thing up to a scale and then get its mass that way, great. If you want to take this thing over here and you want to drop it on your scale and read off the mass that way, bingo, that'll get the job done. If you want to take this thing and you want to drag it with a spring scale and measure the acceleration under a known force, that'll work too. If you want to measure the gravitational mass, that's fine. If you want to measure the inertial mass, that's fine. But we need to know the mass of that box. Otherwise, we can't really know the momentum. We got to know how big the thing is, right? The next thing we have to do is we have to figure out how fast is the box going. So usually, you just say, all right, it starts here, it ends here. This change in displacement took this much time, and that's the velocity. So we could just measure the average velocity, and that'll probably be good enough in most cases. We could take our box and we could put it next to a motion detector, and then we could get a position time graph, and then the slope of this thing would tell us velocity, right? Or we could just probably look at the velocity time graph directly, and then the y value of this would tell us the velocity. However you want to do it, but you have to measure the velocity somehow. Okay. So if we know the mass of the object and the velocity of the object, we know the momentum of the object. So that's one way we can go about doing it. We can just straight up measure momentum by figuring out how fast is that heavy thing going. That's one very straightforward approach to finding our momentum. Okay, cool. That's one way to do it. Hopefully it's not the only way, because that's very narrow. So let's talk about another way we could figure out that momentum. All right. A second way we can figure out the momentum, and pay attention, this part's on your homework like 3 times. Okay. A second way that we can figure out the momentum of the object is by using impulse. So the change in momentum is equal to the force applied on the object times how long that force is being applied for. So let's say I've got that same box and I hook it up to my spring scale and I measure it's got this constant force for this much time. Oh, there we go. That much time. Okay. So to figure out the momentum here, momentum equals force times time. Well, the force is, I don't know, let's say it's 5 newtons. And let's say this is 10 seconds. If I apply 5 newtons for 10 seconds, that's 50 Newton seconds. This is another unit for momentum. The other one, of course, is kilograms meters per second. Either one's fine, right? Newton seconds, because force, newtons, time, seconds. Okay. So we'd have 50 kilograms meters per second of momentum. Let's talk about how I found that, right? Well, I picked easy numbers, first of all. If I'm looking at this graph specifically, a force as a function of time graph, and I don't have a constant force. What if my force is increasing or something? What I'm looking at here, I took this number and multiplied it by this number. That's going to show me the area right here. So we might want to also just keep in the back of our heads, delta P equals area of force versus time graph. Okay. So this would also work if, let's say, we've got a force like that. We've got an increasing force. I slowly pull harder and harder on this spring scale here and slowly bring it up to acceleration. Then instead of looking at this rectangle, I go for 10 seconds. We've got to find the area of this triangle now, which isn't too bad, right? I know the height, maybe that's 6 now. The height is 6, base is still 10. Area of a triangle is 1/2 base times height. So half the base, half of 10 is 5, times the height of 6. This would be 30 kilograms meters per second, right? So if we have a force time graph, the area underneath the graph is telling us the impulse. Okay, disclaimer here, something I want to draw your attention to. This is telling us the change in momentum, not the momentum. So let's say you have a block and it's rolling along, and then you kick on the rocket booster, right? And then we know the thrust of this rocket booster. It's this much thrust, and it's constant for this much time. Okay. Here's my impulse right there. It's that area. If I don't know how fast I was going before the rocket came on, though, I don't know how fast I end. All I know is the change in momentum. That doesn't tell me the final momentum or the initial momentum. It only tells me the change. So if I want to know the momentum, either the final or the initial, I need to know one of these two values also. So I either need to know how much mass it had and how fast it was going at the start. Then using this to find the change, I can figure out the momentum at the end. Or if I figure out how fast it's going at the end and I know the change, I can work backwards and figure out how much momentum it had at the beginning. Okay. But just this alone will only tell you the change in momentum, not the momentum. So just be aware of the distinction there. All right. The last method, and this is one of the most interesting methods, I think, is we can conserve momentum by observing something else. So let's run through this. Let's say I've got this mass. It's got 2 kilograms of mass right here, and it's going 5 meters per second. Don't worry about how we figured that out. Maybe we used a motion detector to measure the velocity. Maybe we've got a cannon that fires things at 5 meters per second. It's not a big deal. We've got a mass going 5 meters per second. It flies behind this curtain, and you hear a loud crash. Right? And then this big thing comes out from behind the curtain. And we go, oh, hey, that's my 5 kilogram thing. And you quickly point the motion detector at it, and you see that the big thing is going 3 meters per second. Wait, what happened to my little ball that I shot at the curtain? Where did it go? Okay, well, let's look at some conservation of momentum. Assuming this thing was just chilling behind the curtain by itself, the sum of momentum initial is going to equal the sum of momentum final. And I'm going to take my system to be everything you see before you. The ball, the beautiful set of drapes, and the other big ball. Initially, I had the little ball flying in. So its momentum would be m1 v1, which are 5 times 2. So we have 10 kilograms meters per second at the beginning. This thing was not moving. So let's hang on. Let me move this around. Sweet, perfect, beautiful. Okay. So we have the momentum of the small ball. Let me even break this down into a few more steps for us. We have the momentum of the small ball initially. That's it. Afterwards, the total momentum of the system is going to be equal to all the momentum of everything in the system, the momentum of this ball, the momentum of this ball, the momentum of the curtains. So we're going to have still the momentum of the small ball. We don't know this, though. How fast is it going? Where is it going? Plus the momentum of the big ball. Okay. At the beginning, just the small ball is moving. Mass times velocity, that's 10. Okay. At the end, we don't know the momentum of the small ball. That's staying a variable. Plus, the momentum of the big ball is m2 v2. 5 times 3 is 15. We're going to take to the right to be the positive direction. So this velocity initial here, this is positive 5 meters per second. The direction matters because, again, momentum is a vector. So we have 15 kilogram meters per second coming out from behind the curtain. So this momentum of the small ball, we can solve for this. Subtract 15 on both sides. The momentum of the small ball is negative 5 kilograms meters per second. So now we can set this equal to the mass of the small ball. It probably didn't gain or lose mass. It's just a ball. Balls don't usually gain or lose mass very often. Times its final velocity. So it has a mass of 2 kilograms. We'll plug that in, 2. Or rather, we're going to divide both sides by 2 to cancel the mass. So our final velocity is negative 2.5 meters per second. So this ball, when it hit this ball behind the curtain, it pushed this thing out. It bounced out. Then this thing bounced off and flew back that way. This one comes out, as we can see here. This one is going to come back out. It's not going to be going quite as fast, not 5 meters per second, but it's coming back out at 2 meters per second. And we know that it turned around because we got a negative velocity, which makes sense. It bounced off. It's going the other direction now. So we can conserve momentum, and then knowing how fast we were going initially, how fast we're going at the end, and the two different masses, we can use that information to solve for how fast is the smaller ball going after it bounces off the big one, which is very interesting. So we don't know a lot about the forces going on here. That's a very mysterious thing. It's probably variable. There are devices we could use to measure it. Maybe not with two balls hitting each other, but we can definitely bounce stuff like off force gauges. Instead of a force gauge being like a scale, or even like a box with a hook and it's like digital, right? Instead of it being like digital, where it's just measuring the pull on this hook here, there are like digital scales like this, right? And then you could like toss a ball onto this scale and hook it up to a computer. Here's our computer right here. Right? And then this scale can spit out a force as a function of time graph. How much force is there happening on the scale? And we'll measure it down to like the millisecond, right? Because it's a computer. Then we can go back to this idea and look at a force times time and find change in momentum. So there's a lot of stuff we can do here. Momentum is very versatile. There's a reason it's one of the infinity stones. It's because using this principle of conservation of momentum and such, we can solve so many problems. It's so useful. So let's go solve a problem, right? I can't. You guys had to know it was coming. I can't teach you something without all reliable. So we've talked a lot about the theory. We've looked at the equations. We looked at how can we measure stuff. We looked at once I measure the stuff, how can I analyze some graphs to figure out momentum? Now let's just solve a problem, right? This is what brought me into physics. I was like, graphs, who wants to set up experiments? Experiments are whack. I didn't care about experiments. I want you to give me a situation, and then without even measuring it, I want to tell you the answer. That's what I think is cool about physics. I don't even have to look at the thing, and I can tell you what'll happen. That's so tight. So, a 10 Newton mass. Notice I said Newton, meaning this is the weight, not the mass of the object. This is, just be aware, right? It's weight, not mass. Is sliding to the right on a rough table. Okay, rough table. There we go. It is initially going 4 meters per second. V initial equals 4 meters per second. Earlier that day, a group of students did an experiment, very nice of them, and found that the force of kinetic friction on this specific mass is 2 newtons. Okay, so notice, again, I'm kind of hand-waving some stuff here. Friction, kinetic specifically, equals 2 newtons. And that's, we're assuming without any added up-down force. Again, if we change the normal force here, if I add weight on top of it, that'll change. But they did some experiments, found some kinetics, some coefficients of friction rather. And then this mass on this table is going to feel about 2 newtons of friction. How much momentum does the block have initially? And how long does it take for the friction to stop? So one of the other great benefits of momentum, because change in momentum, or the impulse, is equal to force times change in time. Unlike energy, which was all positional, how high is stuff? How fast is it going? How much is that spring compressed? None of that had time. Momentum is great because it has time in it. And now questions like this, if we did this with work would tell us how far does it slide with energy. If we use momentum, it tells us how long does it slide for. So again, it's like the other side of that coin from energy. Instead of telling us distances, it helps us find times, which is very useful. So how much momentum does the block have initially? Momentum equals mass times velocity. The mass, okay, the weight is 10 newtons. Weight is mass times g. G is 10, right? So what number times 10 is 10? 1. So the mass is 1 kilogram. Okay, glad we figured that out. And the velocity is 4 meters per second. So 1 times 4, our momentum is 4 meters per second. Okay, so we have, our momentum is not 4 meters per second. Our momentum is 4 kilograms meters per second. Okay, so we have 4 kilogram meters per second of momentum. We want to know how long does it take to stop. What force is stopping our mass? The friction. So our friction is going to cause an impulse and we're going to lose momentum. How much impulse? Well, we want to stop it. So we're going to lose all of our momentum. So the change in momentum goes from 4 to 0. We're going to lose 4 kilogram meters per second. Losing indicated with a negative, right? Final minus initial. final is 0 minus initial of 4, negative 4. Okay. Our friction is 2 newtons times delta T divided by 2. So T is negative 2 seconds. So here's the nuance here, right? Negative 2 seconds. Mr. Barton, I have to go backwards in time 2 seconds? No, I'm being a little sloppy here. Our velocity is that direction. Because I said this is positive 4 meters per second, we're taking to the right to be positive. Which way is friction going to act? Friction is going to go that way, which is the negative direction. So if I were not being quite as sloppy, I would say this is negative 2 newtons, because now that we're looking with vectors, we're working with things that have direction, we really need to be a little more careful with our signs and use those signs to indicate direction. If I don't do that, if I'm just sloppy with it, I slap 2 in there because I see a 2, then we're going to get weird things like you have to go backwards in time. But if we are careful with our direction, force is in the negative direction, negative 2, divide by negative 2, time is 2 seconds to stop. And isn't that just beautiful? All right. Hopefully I haven't been too esoteric and, ethereal about this. Hopefully I haven't been too romantic about it. Not romantic in the sense that, like, you want to kiss your boyfriend or girlfriend or androgynous friend, or probably not. Do androgynous people, by definition, they're not interested in kissing, right? But I digress. Hopefully you got something out of this. If you have questions, please let me know. If you get stuck on the homework, please let me know. If you like this video, then like the video. Hit that little thumbs up button. Subscribe. Tell your friends. Send it to, Newsweek. Be like, my physics teacher tries so hard. Oh my gosh, I appreciate him so much. I'm just so grateful that he puts in all the time and effort and energy to make this meaningful, engaging video for me. If you guys could do me a favor and share. No. All right. Enough pandering. Let me know if you have questions. Hope you enjoyed the video. Have a good day, you guys.